Assalamu alaikum. So today we'll continue with the control of the parent magnet AC machine or the parent magnet synchronous machine. Last time we found the voltage equation in the rotor reference frame, in the QD rotor reference frame, and here if I recall it, VQS equal to RS IQS plus LQ by dt plus omega r LD plus omega r lambda, and VDS was equal to RS IDS plus LD by dt minus omega r LQ IQS. Now here we have cross coupling terms. So here we have the cross coupling term on the Q-axis, and here we having the cross coupling term on the D-axis. Those terms are the interaction between the D and the Q-axis. Now, please note that those terms will complicate the mathematical model, and hence they will complicate the control design. Why? Because simply here we having omega r multiplied by IDS, so simply this means that the cross coupling term are nonlinear terms. So the same thing here, we have omega r a state variable multiplied by IQS, another state variable, so this term is nonlinear term, which will complicate the model and hence will complicate the control design. So the first thing we should think about how we can cancel the cross coupling terms. Now the answer can be found from the feedback normalization. A tool in the control theory states that we can cancel any term using a feedback. So simply how we can do that. So the first step here, so here to cancel the cross coupling terms. So the first thing, let's reshape the voltage. So I will rewrite VQS as UQS, another voltage or another input yet to be designed, and I need to cancel those two terms. So I will add here plus omega r LD IDS plus omega r lambda. So if I substitute VQS here, I will end up with what? I will end up with UQS equal RS IQS plus LQ DIQS by dt, and those terms will cancel the cross coupling terms. The same thing is applicable for the D-axis. So here I will redefine VDS as UDS, a new input yet to be designed, plus, or here minus because I need to cancel it. So minus, I will I will maintain the same sign because I will put VDS in the left half side. So this will be omega R LQ IQS. Now the same thing, if I substitute VDS here, and this one I will do it here. So if I'm substituting, what I will get UDS minus omega R LQ IQS should equal to RS IDS plus LD DI DS by DT minus omega R LQ IQS. So now this term will cancel this term, and we will end up with UDS equal to RS IDS plus LD DI DS by DT. So substituting the new designed VQS VDS in the voltage equation, we will get UQS equal RS IQS plus LQ DIQS by DT, and UDS equal to RS IDS plus LD DI DS by DT. Now those equations represent a symbol RL circuit actually. So those are a simple RL circuit. So those are linear. So we can use our knowledge from the linear contour theory in order to design a current controller. To do so, let's take Laplace transform. So in terms of Laplace, we have the UQS equal to RS IQ of S plus LQS IQ of S, and the same thing here for the UD of S equal to R ID of S plus LD S ID of S. So simply this can be represented by a simple block diagram where the input is the voltage U and the output is the current I, and the transfer function is 1 over R plus LS. So now we can design a current controller using our knowledge. So this will be the I reference, and here I will put small I, and the small I can be either the QX current or the DX current, which means that I'm plotting one plot to represent the two controllers. Now here we should compare it with the actual current, so this will be II. Now here in general we'll use the most famous controller, which is the PI current control. So this is the PI current control, Now the output of the PI current control is the voltage, which is here is the U I, and remember I can be Q or D. And after that I will use 1 over R plus L S, and now I'm having here the output current, which is the I, and here I can feed it. So simply this is a very simple a closed loop current controller. So how I can design the gains of the current controllers. Now if we recall, the transfer function of the PI current control, GC of S equal to KP plus KI over S, which can be written as a DC gain, which is KC, multiplied by tau CS plus 1 over tau CS. So now I'm using a DC gain and a time constant in order to represent the transfer function of the current control. The same thing is applicable for the plant. So let's say GP of S, which was equal 1 over R plus LS. This can be written as 1 over R over 1 plus L over RS. The same thing here. I'm representing the transfer function of the plant of the RL circuit using a DC gain, which is 1 over R, and the time constant, which is L over R. So now, if this is the reference current, I star, and this is a comparator, so this is here minus, and this is I, the actual current, and here I'm using the PI controller, and I will use this representation, which is a DC gain KC, and a time constant, and here I will write tau CS plus 1. Now the same thing here, I will plot the block diagram for the plant, and for that I will use this representation, which is a DC gain 1 over R, and here 1 plus L over RS, and simply this is the UI and this is the II, and remember I can be Q or D, which means that this block actually is 2 blocks. Now if we design tau C, the time constant of the controller, such that tau C is equal the time constant for the electrical part, either if I'm discussing the Q, it will be the LQ over RQ, and if I'm discussing the D, it will be LD over RD. If this is the case, then we having a 0 Bose cancellation, and we will end up with a very simple closed loop transfer function. And here we'll end up with KC over tau CS, and here only we're having again 1 over R and a unity feedback. So if we need to calculate the transfer function for this system, which is the ratio of the output over the input, so I over I star will equal to KC over R multiplied by 1 over tau CS over 1 plus kc over r multiply 1 over tau cs. So now if we need to simplify it, so let's write it here. I over I star, which is the ratio of the output over the input, which was 1 over r multiplied by kc over tau cs over 1 plus 1 over r kc over tau cs. Now this can be written as the DC gain and the time constant, or simply we can say it's 1 over r kc over tau c over s plus 1 over r kc over tau c. So simply I multiplied here by s and here by s, which if you need you can write it as 1 over r tau c over kc s plus 1. So simply here the DC gain is equal to 1 and the time constant, the closed loop time constant, is equal to r tau c over kc. So simply this will equal 1 over tau s plus 1, where tau is equal to r tau c over kc. And now we can design kc to achieve any desired time constant tau, where here tau is the closed loop time constant. So simply now we can plot the block diagram of the vector control for the parent magnet synchronous machine. And for that, the first thing here, let's assume that we already having the power circuit. So this is the DC link, and here this is the inverter, and the inverter is feeding the permanent magnet synchronous machine, and here we are using a tacho generator in order to measure omega r mechanical. So if we multiply by p over 2, we are getting omega r, and if we integrate omega r, we are getting the theta r. So the first thing here, let's assume we are using speed control. So this will be omega r reference, which we will compare it with the actual omega r. and already we have omega r here. And now we will use a PI speed control. So this is the PI speed controller. Now the output of the speed controller is a torque. And here, for simplicity, let's assume that we are discussing a cylindrical machine in which LD is equal to LQ. So simply this means that the torque equation has only one term, which is the interaction between the Qx and the flux. If we recall, here the torque will be proportional with lambda m and IQS, and lambda m is constant, so simply this means that the torque is proportional with IQS. So the output of the speed control will be the reference current IQS star. So this one we need to compare it with the actual IQS. So from where we can get the IQS? Simply from here, we'll measure the A, B, C currents. Then we will use a transformation from the A, B, C to the Q, D with the help of theta R. And now we will get the IQS and the IDS. So this will be the IQS. And after that, here we will use the current control, and this will give us UQ of S. But simply for the machine we need VQ. So here we will add the cross coupling terms, and simply if we recall, we have the following cross coupling terms, which is omega r LD IDS plus omega r lambda m in the VQS. So I will add those two terms to the UQS in order to generate VQS. The same thing I will do, I will subtract minus omega r LQ IQS to UDS in order to generate VQS. So this is the omega r, and I will multiply omega r with the IDS, and this will be the LD, and this is the first cross coupling. The second one is omega r multiplied by lambda m, and this will be the second cross coupling, and this will generate the VQS. Now for the DX, let's assume this is the IDS star, and here, in order to finish the plotting, let's assume that I'm not interested in the in controlling the speed above the rate speed, which means that IDS must equal to 0. And here I will compare it with the actual ID. This is the ID. Then I will use a PI control, and here I will generate the UDS, So now I need to add the cross coupling term, which was minus omega r multiplied by IQS. So this is the omega r multiplied by the IQS, then multiplied by the inductance, which is the LQ, and here it's a minus in order to fulfill the cross coupling term, the feedback generalization that we use in order to cancel the nonlinear term or the cross coupling term on the dx. So this will generate V ds. Now we have VDS and VQS and VDS. So we'll use those. So simply here we having VQS and we having the VDS. So we'll use the transformation from the QD to the ABC with the help of theta r, and already we calculated theta r by the integration of omega r, and this will give the reference voltages VA reference, VB reference, VC reference. Those will go to the pulse width modulation in order to generate the gate pulses for the inverter. So here we'll have the gate pulses for the inverter, and simply this is the block diagram for the vector control of the permanent magnet synchronous machine. So next lecture I will discuss with you the maximum torque per ampere, or how to design the reference current in the D such that we achieve the minimum stator current with a maximum torque. So this is we call the maximum torque per ampere.